Welcome to the All Sorts Podcast. This is The Deep Dive. If you're enjoying this deep dive, please do like, share, and subscribe on YouTube. It really helps us out. Check out our other episodes too, and you can follow us on X, Instagram, and Threads.
And speaking of deep dives, today we're plunging into something truly fascinating, just for you, robots. Specifically, robots operating in the toughest, most challenging places you can imagine here on Earth and even off it.
Yeah, it's a topic that really showcases some incredible human ingenuity,
Yeah.
pushing engineering to its limits, exploring environments where humans just, can't safely go.
Exactly. We've gathered quite a stack of sources here covering a whole range of these extreme situations. You've got the intense heat and maybe toxins in hazardous factories.
Right, all the way to the crushing pressures of the deep sea, the freezing cold of the Arctic ice edge.
The chaos of disaster zones and even the vacuum of space. It's quite a list.
And these sources, they really highlight the different reasons we actually turn to robots when things get extreme. Right. So our mission today is to unpack all this, figure out the key insights into why we send robots into these places, what exactly they do there, and maybe most interestingly, the incredible challenges and the sort of innovations that come from building robots tough enough for these jobs.
And by diving into this with us, you'll hopefully get a much clearer picture of the vital role robotics plays, in keeping people safe, enabling exploration, and maybe even helping with conservation.
Okay, let's get into it then. Let's start with those places that are just inherently dangerous for people to work in day-to-day hazardous manufacturing industrial sites. Yeah. Our sources really detail why robots are becoming, essential there.
The number one reason, it always comes back to safety. Think about workplaces with built-in risks, handling toxic stuff, extreme temperatures, high pressures, working near massive, dangerous machines, or, dealing with radiation.
Yeah.
Things like automated welding in car plants, chemical processing, even just inspecting pipelines in risky areas. They all carry a pretty high chance of accidents or long-term health problems for human workers.
Right, so the robots basically act as a buffer,
Yeah.
taking on that direct exposure. The sources really stress how robots dramatically cut down those risks by working where humans just shouldn't be for long periods, high heat, volatile materials.
Or even just those repetitive tasks that lead to injuries over time.
Exactly.
So they perform these dangerous jobs without putting human health or lives on the line. But it's not purely about safety. There are some big operational pluses, too.
Like productivity, right?
Right.
Robots don't need coffee breaks. They don't get tired.
That's a huge factor. They can operate continuously, 247, in conditions that would just, completely exhaust or even harm a person pretty quickly.
Which means much higher output.
Much higher output and drastically less downtime, even when the industrial setting itself is demanding or sometimes unpredictable.
And what about accuracy? Because human error is always a thing, especially with boring, repetitive tasks or dangerous ones where you might be stressed.
Absolutely. But robots, especially with advanced programming and sensor systems like machine vision, they offer incredible precision, really repeatable performance.
Yeah.
Yeah, their consistency just gets rid of that variability you often find with human labor. That ensures uniform quality control, which is super important when you're handling tricky or hazardous materials on, say, an assembly line. They handle really complex workflows with amazing reliability.
So it allows industries to do things safely and consistently that might just be too dangerous or, too inconsistent if it was humans only.
Precisely. It's enabling tasks that were previously just too risky or demanding for people to do reliably.
Okay, so it's not necessarily about replacing people across the board, but more about enabling, totally new levels of safety and efficiency for jobs that are just too much for humans.
Exactly.
And that leads us pretty neatly into disaster response, another situation where environments suddenly become incredibly hazardous and unpredictable.
Oh, yeah. Disaster zones are pretty much the definition of extreme environments. They're chaotic, unstable, often toxic, or just physically impossible to get through. Robotics is playing a really crucial role across the whole disaster management cycle, from the first look to search and rescue and even long-term recovery.
I've definitely seen those pictures of drones flying over collapsed buildings. Our sources mention UAVs, unmanned aerial vehicles, and UGVs, the ground ones being critical.
Yeah.
What specific jobs are they doing?
Well, the UAVs, the drones, they're invaluable for that quick aerial view. They can rapidly scan damaged areas, send back real-time video and data.
So first responders know what they're facing.
Exactly. They understand the scale of the damage, identify where help is needed most urgently, maybe spot where survivors might be. Then you have UGVs, the ground robots. They can actually navigate through rubble, go into unstable buildings.
Places too dangerous for people.
Right. Or just too difficult to reach. It minimizes the risk to the human rescue teams themselves.
And they can carry supplies in too, can't they? Like essentials.
Absolutely. They can deliver small packages, food, water, medicine, maybe communication devices to people who are cut off, where roads are blocked or infrastructure's gone.
Okay.
They can also monitor the environment itself, tracking air quality, temperature, even radiation levels after something like a nuclear incident.
Yeah.
That keeps both the rescuers and the affected population safer.
And then later, for recovery, I guess they help with inspecting damaged infrastructure, bridges, buildings that might not be safe to enter.
Yes, or even helping with the cleanup, like decontamination of hazardous materials left behind.
It really seems like without robots, a lot of these critical tasks would be incredibly slow or way too dangerous, maybe even impossible.
Definitely. It boils down to speed, safety, and getting eyes and tools into those really inaccessible and risky spots when every minute counts.
Speaking of inaccessible and risky, let's shift gears to maybe the most iconic extreme environment for robots. Space. What is it that makes building a robot for the vacuum, the radiation, the crazy temperature swings of space so incredibly difficult?
Well, space is just this perfect storm of extreme challenges, really. First off, the environment itself is brutal. You've got intense radiation bombarding everything, which can fry electronics.
Right, that needs that special radiation hardening you hear about, which sounds expensive and complicated.
It is. Very. Then you have these massive temperature shifts. You could be looking at like minus 150 degrees Celsius in shadow, then swing up to over 120 degrees Celsius in direct sunlight.
Wow. How do you even manage that?
Sophisticated thermal control systems, active heaters, radiators, layers of insulation, special coatings, all just to keep the sensitive electronics working within their happy temperature range. And then there's the new vacuum, which affects materials, lubrication.
And dust. I remember reading about the Mars rovers and the dust.
Yeah, that fine clinging dust like on the moon or Mars. It's abrasive, it degrades surfaces, it can clog up moving parts, and it even cuts down the power you get from solar panels. That was a persistent challenge for the Opportunity rover throughout its amazing long mission.
So you need unbelievably tough materials and mechanisms that can just keep going without any chance of, popping out for a quick, clean, or regular maintenance.
Which leads right into the second huge challenge: autonomy. The communication delays are just immense. Sending a simple command to a Mars rover might take, 20 minutes to get there?
And another 20 minutes to hear back if it worked.
Exactly. You absolutely cannot be manually driving a rover around rocks with a 40-minute round-trip lag. It's impossible.
So they have to think for themselves, essentially.
Pretty much. Robots in space need to be highly autonomous. They have to navigate, analyze the terrain, spot hazards, make quite complex decisions, all on their own. Perseverance, for instance, uses really sophisticated autonomous driving software. It plans its own routes, avoids obstacles, even picks scientific targets with minimal human input day to day.
That sounds like incredibly complex software for perception and decision-making. And it has to work even when it runs into something totally unexpected, like a weird rock or a sudden steep slope.
And adding another layer of difficulty, the processors they use in space are often less powerful than, say, the chip in your phone. They prioritize reliability and radiation tolerance over raw speed.
So engineers have to be super clever with optimizing the software to run these complex AI systems on relatively limited hardware.
Absolutely. Building a space robot is this incredibly complex balancing act. You need it physically indestructible, highly intelligent, and autonomous, but also working within strict limits on power, processing capability, and of course mass, because launching stuff is expensive. It really is an amazing feat of engineering.
It truly is. Okay, let's pivot now to a very different kind of extreme environment, the natural world, and explore something fascinating our sources cover, using bio-inspired robots for conservation work.
Yeah, this is really interesting. Our sources point out that sometimes traditional conservation methods led by humans can actually have some downsides.
Like using noisy helicopters for wildlife surveys. That could disturb the animals, right?
Yeah.
And pollute sensitive areas.
Exactly, or even just vehicles driving through delicate landscapes could accidentally harm small animals or damage plants.
And they're just places that are incredibly hard, maybe impossible for humans to even get to for study or monitoring, like deep ocean trenches, remote caves.
Dense rainforests or treacherous polar regions, just too difficult or dangerous for direct human access.
So this is where robots offer some unique advantages. Drones, UAVs, can quietly scan huge forest areas, track marine animals like whales without stressing them out, or explore cave systems.
And underwater vehicles can get close to marine life at depths and for durations far beyond what a human diver could manage. Terrestrial robots can survey tricky landscapes like active volcanoes or unstable glaciers.
But even standard robots, like wheeled ones, can have issues in nature, right?
Definitely. Wheeled robots can get stuck on uneven ground or soft surfaces like sand or mud. Propeller-driven underwater vehicles can stir up sediment, making it hard to see, or could even pose a risk to fragile aquatic life. Noisy drones might still disturb certain wildlife.
And those standard rigid robot arms aren't exactly great for delicate interactions.
Which is precisely where bio-inspired robots start to look really promising. Instead of just wheels or propellers, they take inspiration directly from nature. How animals move, how they sense things, how they interact with their surroundings.
So not just copying the look, but the function.
Well, you have biomimetics, which does try to copy natural forms closely, but also bio-inspiration, which is maybe more about understanding the underlying principles, focusing on how a natural system works, not just what it looks like. The aim is robots that can move and sense more like animals do to minimize disturbance and navigate those complex natural environments better.
Like that salamander robotic at the sec you mentioned that walks and swims like a salamander. Or robots designed to move like fish or birds or even insects.
Exactly. These designs give them enhanced movement abilities suited to specific places. Robots that can walk on sand or snow, climb walls, perch quietly like a bird to save energy.
Or run along the seabed.
Yeah. For underwater stuff, mimicking fish allows for smoother, quieter movement than propellers. And designs like those soft, snailfish-inspired robots can handle the immense pressure in the deep sea.
And for those delicate tasks, like maybe carefully handling an animal to tag it or give it medicine.
Soft robotic arms with tactile feedback are much gentler and safer than the traditional rigid metal ones.
So beyond just moving like animals, what else do you need to consider when deploying robots out in the wild for conservation?
Well, durability is obviously key. Conditions out there are rugged, unpredictable, so there's research into adaptive structures using high-performance materials, and even this really fascinating field of self-healing materials.
Robots that can fix themselves. That sounds pretty sci-fi.
It's getting closer to reality. It could mean robots that operate autonomously for much longer in remote spots, potentially reducing electronic waste and costs, too.
What about the brains and sensors? Does bio-inspiration play a role there, too?
It does. Biological intelligence is known for being adaptable, robust, versatile. So you have things like neuromorphic computing, which tries to mimic the structure and function of biological brains' neural networks to allow for faster, more adaptive responses to dynamic environments.
Okay.
And then there's swarm intelligence.
Like a school of fish or a colony of ants all working together?
Precisely. Using lots of simpler robots that coordinate with minimal central control or communication, they work together to achieve tasks a single, complex robot couldn't manage alone.
What kind of tasks?
Think about monitoring really large, complex things like mapping a vast area of ocean pollution or tracking animal migrations over a huge region. The Kokoro project, for example, used an underwater robot swarm inspired by fish schooling.
And energy is always a big constraint for robots, right? Especially small ones out in the middle of nowhere.
Definitely. Batteries are the standard, but researchers are looking at alternatives with higher energy density like hydraulic fluids. And a big focus is on energy harvesting, pulling power from the environment itself.
Like solar.
Solar, thermal, even kinetic energy from movement, or wireless energy transfer. Anything to extend autonomy. There are even experimental robots like EcoBot 3rd.
The one that eats.
Yeah, it has a microbial fuel cell system. It can power itself by basically digesting organic matter.
Wow, using a digestive system for power.
Yeah.
That's really thinking differently.
It really pushes the boundaries.
Yeah.
And one final point for conservation robots thinking about what happens when they stop working, their end of life. If a small robot, maybe part of a swarm, fails in a sensitive ecosystem and you can't easily retrieve it.
You don't want it just sitting there polluting the place.
Exactly. Ideally, it should safely biodegrade over time.
So making the structure out of materials like cellulose or PLA plastic?
Right. The big challenge is making the electronics and the power source biodegradable too. Progress is being made, like with those microbial fuel cells, MFCs, even though their energy output is still quite limited. Another interesting idea is using actual living organisms as sensors like lichens or mussels, either on the robot or alongside it.
Using nature itself as part of the sensor system.
Yeah, reducing the reliance on non-biodegradable electronic components.
You know, this deep dive has touched on so many different extreme environments. Factories, disaster zones, space, natural ecosystems. But it feels like the basic challenges in building robots for them, they share some common ground.
Absolutely. It always comes down to designing for resilience and functionality within very specific and often very harsh constraints. For robots on land, it's about handling incredibly varied and unpredictable terrain, loose sand, deep snow, thick vegetation, unstable rubble after a disaster.
Right. And aerial robots, they have to fight gravity, deal with wind, but maybe also need to perch somewhere to save battery or glide silently so they don't disturb wildlife.
Exactly. And underwater robots, they face that immense pressure increasing with depth, corrosion from saltwater, often terrible visibility, managing buoyancy and drag.
And sensing things in water, which is obviously very different from air.
Precisely. That demands robust, watertight electronics, materials that resist corrosion, and sensors adapted for murky or low-light conditions. Often mimicking how marine animals do it, like seals using whiskers or fish, using their lateral lines to sense water movement. That soft snailfish robot we talked about is a perfect example of designing specifically for extreme deep-sea pressure.
It seems pretty clear that solving these really complex problems needs a lot of collaboration. You need engineers working with biologists, conservationists, material scientists.
And crucially, the people who will actually be using these robots out in the field,
Yeah.
engineers need that biological insight to understand how nature provides effective design ideas. And biologists or conservationists need roboticists to build the specific tools they need for their research or work. Involving local communities where these robots might be used is also really important for building trust and ensuring sustainability in the long run.
And practicality has to factor in too, right? Conservation projects especially often run on tight budgets.
Definitely. So designing for cost effectiveness, maybe using off-the-shelf components where possible, modular design so you can swap parts out, even open source technology, all that can lower the barrier to entry and make these powerful tools accessible to more people.
We are starting to see some commercial examples pop up too, aren't we? Like those four-legged robots, Spot or ANYL.
Yes, which shows that the capabilities first developed for these really extreme environments are beginning to filter out beyond just pure research labs. Though you're right, cost is still a major hurdle for many potential users right now.
What I find really fascinating, though, is how these bio-inspired robots aren't just passive tools for collecting data or doing simple tasks. They could potentially become, like, interactive agents within these environments.
Yeah, this is leading into some really cutting-edge areas, sometimes called ethobotics or organismic augmentation. It involves using robots designed to look or behave like animals to actually interact directly with wildlife.
To study them, or even influence them.
Both, potentially. Like using robotic fish, robofish, to swim with real fish and understand schooling behavior from the inside. Or a tiny robotic bee, robo-bee, to study how bees communicate within a hive.
Or that really intriguing idea from the sources about integrating robots into animal societies, or using them to subtly nudge ecosystems in a certain direction. They called it ecosystem hacking.
It's about leveraging that animal-like form and behavior, using the robots to understand complex natural systems from within, or maybe even guide animal behavior in beneficial ways, like using robot wolves near farms to scare off real predators, or perhaps helping train captive animals before release.
Okay, so pulling this all together, what does it all mean? We've explored how robots are, well, way more than just tools for making factories run better. They're becoming essential partners in dealing with serious risks, exploring places we just can't reach on Earth and beyond, and even helping us study and conserve the natural world in ways that are less disruptive.
Yeah, we've seen the incredible engineering that's needed to make them withstand everything from radiation and insane temperatures to crushing pressure and impossible terrain. And often the cleverest solutions are inspired directly by nature itself.
So here's where it gets really interesting and something for you to think about. When we consider these bio-inspired robots, the ones designed not just to move and sense like animals, but potentially to interact with wildlife, maybe even influence their behavior or entire ecosystems, it raises a really fundamental question, doesn't it?
It really does.
As these robots become more integrated into sensitive natural environments and interact more directly with living things, what are the ethical considerations we absolutely need to grapple with? How do we ensure their use is truly responsible, transparent, and ultimately trustworthy?
That is indeed a very important question to ponder. It forces us to think beyond just the technical possibilities and consider the wider impact, the principles that should guide how we design and deploy these increasingly sophisticated, almost lifelike machines.
Definitely something significant for you to mull over. This deep dive has, honestly, only scratched the surface of this huge and exciting field. But hopefully it's given you a much clearer picture of the vital and constantly growing role robotics plays in operating where humans simply cannot or should not go.